Hello, everyone, and thank you for joining us today for the second part of our pressure vessel seminar. My name is Nicco Floresca, the Inside Technical Sales Supervisor for the Filtration Division. We have our panelists here. We're joined by Aniruddha Deoghare, who is our Applications Engineer, Richard Jacobs, our Engineering Manager, and Anita Gupta, who is the Business Manager for the Filtration Division of John Brooks Company. Today, we'll be delving more into the design side as it pertains to the code or directive required for fabrication, testing, and inspection of pressure vessels. Note that microphones will be muted. However, you have a means to input questions via the taskbar in the bottom of the Zoom application. As there's a fair amount of content to go over here, we'll do our best to leave some room for questions. If time does not permit, we will answer them offline and send our responses to you along with the recording of the video. On to a quick introduction into John Brooks Company. We are a privately held Canadian company, and proudly Canadian, founded in 1938. We have presence across all of Canada with over 200 employees. And we've since grown to be a full-service supplier of pumps, filtration equipment, spray nozzles, valves, custom skid packages, heat exchangers, compressed air purification systems, and pressure vessels. Here is an overview of what we'll be discussing today. First is a brief snapshot into the ASME boiler pressure vessel code and the sections within it, also how it compares against other pressure vessel codes. Then CSA B51 as it pertains to vessels fabricated for installation in Canada, finite element analysis, the various types of NDE, and the codes detailing that govern NDE, and then destructive testing, and finally, questions. Bit of a history on how the ASME pressure vessel code came to be first. So the American Society of Mechanical Engineers were first founded by these three gentlemen here, over the need for a unifying body to aid in the design and development of standard tools and machine parts. As industrialization led to increased use of steam boilers, there were unfortunately many incidents that led to either injury or death that warranted the eventual formation of the ASME Boiler Pressure Vessel Code in 1915. Here we can see how the ASME Boiler Pressure Vessel Code was first tailored for the industry at the time into the 1930s with respect to the use of boilers, including, you can actually see here, section 3, it used to be locomotive boilers. Over the subsequent years, with the acquisition of new knowledge, information, better fabrication processes, better testing methodologies, the code has since grown to 12 sections. And you can see kind of the changes that's been made. So locomotive boilers are no longer there, and nuclear facility components have since been added. And it should be noted that there's always a tailwind when it comes to safer and sound design, and therefore the code is actually updated every 2 years to ensure that the code incorporates new findings. To recap the previous webinar on the ASME Boiler Pressure Vessel Code, its purpose is to help provide requirements as it relates to the design, fabrication, inspection, testing, and certification of pressure vessels at either internal or external pressures. For the purpose of this seminar, we'll be focusing on the pressure vessel side, which is section 8. And section 8 is comprised of 3 divisions. Division 1 is the most commonly used all over the world. Division 2 is specific for what's called as engineered pressure vessels, and this requires additional methods for stress analysis. It also has a more elaborate scope of non-destructive examination and increased protocols on fabrication and material control. You can also see that it has a higher operating pressure allowed as well. And then section 8, Division 3, it's specific for designs that are over 10,000 PSI. When we're comparing different pressure vessel codes now, we'll be looking at divisions 1 and 2 only in this case, as we are not getting into high design pressures over 10,000 PSI for division 3. And CSA B51 is listed here. It's not necessarily a different pressure vessel code in the sense that it actually adds upon the ASME code and provides clarifications. As an analog, perhaps for those familiar with the Canadian Electrical Code, its short form is actually CSA 22.1. So in this case, for boiler pressure vessels and piping, it's CSA B51. Then we have the European Pressure Vessel Directive, EN 13445, and what this actually is, it consolidates a number of parties, nations, British, Dutch, German, and French. And as you might imagine, it can be difficult to navigate through this code, as it actually points towards different other codes that it's difficult to acquire. And that's partially the reason why ASME is preferred, due to the ease of navigation. And then finally, we have the pressure PD 5500, which is the British standard. It's now superseded by the European Pressure Vessel Directive. However, there are still countries that do utilize PD 5500. And to make it easy to digest, here are a few primary differences that you might run into for these pressure vessel codes. Among them are material selection. So it could be restricted to ASTM material or EM material, for example. We have allowable stresses, joint efficiencies, safety factors. For example, the safety factor for Division 1 is 3.5, whereas Division 2 is 3. We'll be looking at allowable stresses specifically in the next example. A good way to visualize how maximum allowable stress varies across different codes is to look at a generic stress strain curve for a material. And you can see here a number of areas labeled. The ones of interest would be the yield point. And this is the point at which the material exits its linear stress strain pattern and enters a irreversible stress, or where permanent tensile deformation would occur. And this is called the plastic range, you can see here. Before the yield point is when we're able to have the material return to its original shape when the applied stress is no longer present, and this is called the elastic range. We also have the allowable stress designated here, which is governed by, in ASME's case, section 2. You can see it here. Now, when comparing different codes, we have a better visualization of where they may be placed with respect to maximum allowable stress. And you can see where the other design codes would place themselves on the stress strain curve. And it's shown here that Division 1 is actually lower than most other codes. And this inherently allows a larger design margin. Hey, Annie, since we're jumping into a couple calculations examples soon, it's to my understanding that part of your interview process was rather unconventional in the sense that you were asked to perform code calculations. Oh, Annie, I think you might be on mute.
Yeah, Nicco. It was a great experience when I first met with you and Anita during the interview process, and asked me to perform complex calculations for some air receiver, which John Book was quoting that time. And it was a rewarding feeling that something you are designing has come for production and fabricated as we speak.
Okay, great. Thank you very much, Annie. So since you're the subject expert here, I will be relying on you to correct me if I stumble here. And we'll be now segueing into a couple of sample calculations. We'll be taking a look at a couple parts of the vessel, in particular the shell and the head. The shell thickness and maximum allowable working pressure are governed by these calculations, right, Annie?
Yeah, correct.
Okay, all right, I'm doing well. Let's get into an example now that Annie gave me for homework last night. Okay, so these are the design conditions that we would have to input into those previous equations. Now let me get my pen and paper. Okay, design thickness, all right. Plug in the numbers, multiply, add that. Okay. Annie, does that look good to you?
Yeah, for the design pressure of 200 psi and the diameter of outside diameter of 38 inches, you will get the thickness of this 0.0159 inches. This is the minimum design thickness for that particular shell. So you need to choose the thickness, next available thickness in the market.
Okay. Thank you, Annie. On to the maximum allowable working pressure now. This is the formula that we have to use. Plug in the numbers. Okay. Annie, does that look good?
Yeah, this is the maximum allowable working pressure. So you need to calculate the maximum allowable working pressure for each component in the pressure vessel, which will decide the maximum allowable of working pressure for that vessel, which is the weakest, which is depend on the weakest component of maximum allowable working pressure.
Super. Okay, we'll get into that note now for the semi-elliptical head. And this is the formulas that we would have to use. And we have, now that we have this in our toolbox, let's go ahead for the semi-elliptical head. And it's the same design conditions as prior. And this is the design thickness. So we got that. And we actually are just jumping now into the maximum allowable working pressure. And based off the thickness and the maximum allowable working pressure, as Annie had mentioned prior, the weakest component in this case right now, based off the design or maximum allowable working pressure, is the head, because this is less than the shell allowable working pressure. This is but a brief glimpse into the calculations into the ASME code vessels. We do now have software that does speed up this process, and we'll actually go over an example here. As an example of what was done for software, you first have to design the model, input the permanent parameters, material design, pressure, design temperature, minimum design metal temperature, are inputted into the program, and then you'll get something like this. If you recall the thickness and the maximum allowable working pressure that we calculated earlier for the shell, it actually matches. And since we're now familiar with some of the code calculations, let's see how they compare amongst other pressure vessel codes. To better emphasize the differences or lack thereof, here's a quick sample calculation to determine the thickness of a shell. And weld efficiencies are omitted here for easier comparison. But as you can see here, the difference is negligible for division 1 and 2. However, remember that division 2 may call for additional testing on top of what division 1 calls for. The difference in thickness is made larger when dealing with higher pressures due to the way that the equation is set up. But in this case, the preference would be ideally division 1. And then we have the European Pressure Vessel Directive formula for calculating the shell thickness. And you can see there's quite a difference here. Now, contributing reasons, as mentioned earlier, could be the type of material selection, allowable stresses, joint efficiencies, or safety factors being applied. On to CSA B51 now, and as how it ties into the CRN aspect. Here's an illustration of what the CRN actually means. And what the CRN provides is that it's a confirmation that the vessel conforms to CSA B51 requirements. And the format is such that it starts with a letter, followed by three to five digits. And these alphanumeric values are essentially the registration file number for the technical authority that has the design registration. And that is then followed by a dot and the first province which it was registered under. In this case, it's actually Alberta. And it's then followed by subsequent provinces it may have been registered in. And here's the format of the numbers and letters you may run into. Now, if the vessel or fitting is registered across Canada, the letter C would denote that to be the case. although you still have to have the province that it was first registered in, who would do that registration across Canada. Now, on to the question, when do we have to register our vessel? And you can see here, it might be a bit overwhelming, but there's a number of decision trees to help guide in that decision making. And it depends on a few conditions, whether, for example, whether or not the liquid fluid is more hazardous than water, non-lethal gas or vapor, or non-lethal liquid not covered in the previous. And lastly, we have vessels containing lethal substances, which is this. Say we go through figure 1B, and from the design pressure, we find our design pressure is over 15 psi. The vessel will invariably have to be registered, and the subsequent steps would then help us determine whether it needs to be registered as a fitting or as a pressure vessel. Let's say it has to be registered as a pressure vessel. What do we have to do next? When applying to register a new design, there are requirements set forth by the regulatory body you'd be working with. And just an example, let's look at ABSA, for example, or the Alberta Boiler Safety Association. Here's a list of what would be included as part of the package. And once the application is received, it's assigned to a surveyor who will then review the design, and if there's no hiccups, they will approve the vessel for registration. Okay, that was easy. After all that waiting, now we can start fabrication because we have CRN, right? That's not necessarily the case. More often than not, procurement and fabrication begins in earnest once the vessel design is reviewed, certified, and stamped by a professional engineer. It's then released for purchasing fabrication by the quality manager. And because the approval of the design registration may be in the order of several weeks, it's necessary to begin early to reduce the delivery time. And this relies on the fabricator being confident in their design, which stems from their experience with the code and the wisdom gained in similar designs. Note that this CRN submission was contingent on calculations that were able to be garnered from the ASME code. And the reason I say that is you may ask Nicco, but what about certain vessels that may not be easily analyzed via ASME calculations? We'll get to an example now. Excuse me. You have a vessel here that has a casting to form the inlet head assembly. There's no formula available in the ASME code to cover the shape, so we have to do something called finite element analysis. Let's take a closer look here. And performing finite element analysis requires actually a fair bit of computer horsepower, and any way to reduce that number of calculations to help the program converge faster helps. In this case, the model is split in half due to its symmetrical design. And simplification of geometry whenever you're doing FEA has to be justified. And in this case, the fact that it's symmetrical, the loads are symmetrical, you're able to pretty much cut it in half. And once a number of other parameters are inputted, a mesh is laid over onto the design as such. And you can see here a tetrahedral mesh is used, and it's about a 1/4 inch in size, and then the mesh is further refined or made smaller at the head component to produce more accurate results. And I actually mentioned here which part of the CSA code describes the requirements for FEA. Once everything is said and done, you will have a report that will include, among others, a stress plot. And this plot has a description with the color separation for the stress ranges. And what we find here is that the castings are proven to be suitable for use as the values are under the maximum value here are under the allowable stress of the material being tested. In this case, this is stainless steel CF8M cast steel. With that, you ought to have confirmation on the report that confirms the design complies with ASME requirements, and the analysis and report may be used as an aid for design registration. There's other important results not noted here, such as resultant displacement, reaction forces, etc. So it's important to know this is just a small picture. And now that we have that, presumably you'll be able to get CRN. We'll be switching gears now into the non-destructive examination aspect. And what this covers is the different types of NDE, the applications, for example, radiography, ultrasonic, liquid penetrant, mag particle, ferrite testing. And NDE is an integral part of the overall pressure vessel process, as it allows inspection of components without altering the material. That's a key thing here. And it's purposed to detect internal imperfections and provide quantitative and qualitative measurements that could be used, that could be potentially out of tolerances. So it has to be a criteria that has to be inspected. And it must be noted that the extent of NDE is usually determined by code, design, or if the customer requirements. And whomever would be doing the NDE, it's important to note that they would have to be certified by whatever provincial regulatory body that the inspector is located in. And this ensures that they're following the regulations within ASME Section 5. As we have to be familiar with different welded joint types, we'll be going over them quickly per this illustration. First, we have category A, which is longitudinal welds. And you can see in this case, we have them labeled accordingly. And then we have category B, which are circumferential welds. And then category C and D are primarily for nozzles. And you can see that they're welds from the pipe to flanges and head to flanges for category C, for example. And for category D, this is for nozzle pipe to shell. And we'll be going over an example here and how it applies. So let's take a look at a vessel here and how we assign those joint categories. This vessel also seems to be a jumping jelly bean. First, from this view, we can identify a couple points. Category B are the circ joints here, as noted as green. Category D are the red ones here, which are the nozzle to shell joints, and nozzle to head joints as well. And if we want to look at the other joints, we're going to have to reorient this. Oh, okay, it's still jumping. And now we can see the category A welds, which are the longitudinal welds, highlighted as yellow in this case here. And then we have category C joints for the flange to pipe connections. They're a little bit hard to see. However, in the bottom, these are the nozzle to pipe connections right here. And it should be noted that there would also be a category C weld here for this flange to the pipe connection here. The next concept we need to be familiar with is joint deficiencies. And you'll have seen this actually used in the previous calculations. The variable in this case was E. This determines the material strength. Joint efficiency is used as a measurement of the welded joint with respect to how close it is to its material strength. And without implementing certain tests or inspections, the joint efficiency of a welded joint is actually less than the parent material. And it's something that per conducting tests, you're able to bump that joint efficiency up by verifying the weld. And we'll see how this applies in a bit as it relates to radiography. Now, the requirement for radiography is driven by this code, UW-11, and we'll be first looking at X-ray as the source of radiation specifically. And this X-ray is actually not so different than what you would see at a doctor or radiologist, where you have the X-ray source that points towards an object of interest and the film behind it is exposed. There's other sources of radiation available, such as radioactive isotopes, iridium-192, selenium 75, and it's used in certain cases. However, the preferred radiography method is X-ray. And radiography may actually be conducted before and or after post-well heat treatment. Though note that other NDEs would be likewise, they can be done before and after post-well heat treatment, depending upon the design or customer requirements. And below, we have a few configurations that are employed when conducting radiography. You can see the setup of the radiation source actually positioned and the film against the weld of interest being radiographed. Now, why do we radiography in the first place? The purpose of radiography primarily is to have a quantitative and qualitative measurements of any faults or imperfections of the weld. And by doing so, that infers the joint efficiency of that weld. Hey, Annie, as a general rule of thumb, have you seen situations that you see quite commonly where radiography is required?
Thank you, Nicco. As per ASME Section 8 Division 1, there are many instances where full radiography is required, given in UW11 as stated here. More likely for all the butt welds of pressure vessels, which is used to contain lethal substances. All the butt welds in which your nominal thickness exceeds certain thickness based on the P number of that material. Like for carbon steel material, table UCS 57 provides various thickness criteria in which full radiography is required. Most commonly used carbon steel material like SA516 grade 70 need full radiography when its nominal thickness is more than 1¼ inch. Also, full radiography is required in steam boilers when your design pressure is more than 50 psi.
Okay, thank you very much, Annie. So this is something that again, it is important to always refer to the code, as there's minor nuances that you have to be mindful of when you do have to implement radiography. And the end result of that X-ray would yield a film such as this. And in this case, the welded joint would not be acceptable due to the film showing a lack of penetration. You can see here as the dark line in the developed X-ray photo. And a report would accompany this as what we have here. Although, sorry, it should be noted that this report is not associated with this film. And it will identify which weld joints are acceptable. And if they are not acceptable, it will disclose why they're not. However, it should be noted that in some cases, it can still be acceptable, even though there are notes here, because it still meets within, there are certain limits that you can still be deemed as acceptable. Now, what effect does this radiography have on joint efficiencies? We mentioned it earlier, and here are a couple instances where you can see actually where the radiograph is done and what that does to the joint efficiency. So for full radiography or RT1, you have joint efficiency of 1. In other words, 100% joint efficiency. RT2, you have a different configuration now where there's only spot welds on the circumferential welds or category B welds, and then there's a radiography on the full length of category A welds or the longitudinal welds. Now RT3 is all, for the most part, it's all just spot radiography on category A and B welds. And it allows a joint efficiency, in this case, 85% for all joints. And then lastly, we have spot radiography for category A only. And you can see here that it only allows for a 85% joint efficiency for the category A welds. And then B, it remains the same as 70%. Now, Annie, if you can please add some detail actually on the radiography options, because I know it's important in the software, and what options do we have?
Yeah. In complex calculations, there are all the options available for radiography, like full radiography, spot radiography, and even no radiography, as per Section 8, Division 1, UW11. So you need to choose any one option based on your requirement.
Okay, thank you very much, Annie. On to the next type of NDE, which is ultrasonic testing. And it's similar to radiography, actually, in a sense that the requirement for ultrasonic testing is governed by the same section. Again, UW-11. And it fulfills a similar purpose as radiography in that it's used to detect internal defects and measures material thickness. And ultrasonic testing may also be employed to confirm joint deficiency of the joint. Now, a caveat to ultrasonic testing is that it may be difficult to implement on a stainless steel vessel due to the fact that whenever the ultrasound encounters the stainless steel material, it encounters severe attenuation, and that could lead to incorrect readings. And that's why it's actually preferred for carbon steel. And we can see the setup here where it is employed. You have a transmitter and then a receiver. This configuration is typically employed, and now we're going to be looking into how that might have be implemented in a report. So we'll be looking at an example here of an ultrasonic test used to measure thickness. And prior to the inspector conducting the test, the designer would have to identify the areas of interest. You can see here where they're labeled. And then upon completion of the ultrasonic test, you would receive a similar report to the right, which indicates the thicknesses that were garnered from the ultrasonic test. And this confirms the measured thickness that it in fact meets the minimum thickness requirements in the design calculations, similar to what we've done before. On to liquid penetrant testing now. And liquid penetrant is actually one of the most popular NDEs. It's frequently used due to its friendly procedure and guidelines, and the requirement is laid out in this particular section of the ASME code. And we also have a list here of some parts that would be employed if the code requires, and depending if certain criteria are met. And to conduct a liquid penetrant test, here's a figure to illustrate what needs to be done. The surface must first be prepared. You wouldn't want to do a test that still has rust, scale, spatter, dirt, etc. on it. And once the surface is prepared, we can then apply the penetrant, in this case here, and then through capillary forces, sorry, this is the penetrant here, and then through capillary forces, it penetrates, hence the name penetrant, into these surface imperfections. And then once the surface is cleaned, the excess penetrant, a developer is then applied, which over time, it will change in color, as you can see here, as red. Yep. And now on to magnetic particle testing. It's actually similar to liquid penetrant testing, and magnetic particle examination is frequently used as a NDE method, owing in part to its low cost to perform the test. However, it should be noted that it's only contingent on the material being ferromagnetic. If the material cannot be magnetized, then this test won't work. And mag particle testing, it checks for surface discontinuities, but it actually also reveals discontinuities slightly below the surface. And you can see here the figures below where it's a magnetic field is being ran through a material. So the top one, they're nice and straight. However, once we have a defect, as you can see in the bottom figure here, you can see that the magnetic field is altered. And by then adding magnetic powder or particles, they're able to adhere to that surface, giving a quick visual check to verify discontinuities. So mind you, there are other NDEs. We're barely scratching the surface here. There's, for example, ferrite testing, PMI. It's something that, in the interest of time, we'll be covering at a later point if you would like. Now on to destructive testing. There are various other destructive testing that may be done. But in this case, we'll be looking at impact testing specifically. The other destructive testing, just for your interest, could cover, for example, tensile testing, hardness testing, proof testing, or burst testing. And for this particular case, again, impact testing, we're looking at it specifically as it's important because it's of its relation to the minimum design metal temperature or low temperature designs. And impact testing, what it actually is, it tests the amount of energy absorbed by a material during fracture. And this energy that's absorbed is a measure of the given material's toughness. And it acts as a tool to evaluate the material's behavior in the temperature-dependent ductile brittle transition. And impact testing is infrequent for the most part in industry, though when it is required, it is an expensive endeavor for multiple reasons. And more often than not, that's why you'll see in pressure vessel drawings, you'll see an exemption noted as listed here, denoting the fact that it will not be required to conduct impact testing. Now, if your design does not meet the criteria in the ASME code, which is UG-20F, this is, you would then move on to UCS 66, various other steps involved if you were not exempt, though once they're exhausted and you do eventually find yourself exempt, it would be noting this particular case. Now, as an example, we're looking at a thickness here for 1.5 inch. The material used is SA 51670. This is normalized carbon steel, and the minimum design metal temperature is -20. And by following what I had mentioned earlier, this design will actually not pass UG-20F. So we have to move on to UCS 66. And once we kind of do a match based off the thickness, the MDMT, you find you still do not pass. Now, it's then leads to another parts of the code that eventually you will find that you are exempt to the impact testing. Now, if the vessel were to be purposed for install in Canada and say the minimum design metal temperature were to be less than -50 degrees Fahrenheit, we actually have no choice but to conduct impact testing. And with that, we open the table here for questions. And again, it should be noted that we had covered quite a bit of content here. And we've only scratched the surface. This is the tip of the iceberg, so to speak. The ASME boiler pressure vessel code is actually, all these sections are north of over, I think, 16,000 pages. And that's why it's important to work with designers, fabricators that are familiar with the code and have licensed engineers in their retain and have fabricators that hold an ASME certificate of authorization. So.
Thank you, Nicco. There are a couple of questions. If you don't mind, should I go ahead and put some questions there?
Yes, actually, Richard, I just want to make sure that you're able to talk.
Yeah, Richard is unmuted as well. Yeah, and actually,
I'm here. Can you hear me?
Yes. Yeah.
Okay.
And if we need, we also have our shop manager online. We can also, allow him to talk at some point. So let me start. The very first questions here is, what's the difference between working pressure and burst pressure? Nicco?
Yeah, Annie, if you would not mind, please, Ashley, please answer that.
Yeah, so as per my knowledge, working pressure is the operating pressure we are of the fluid inside the pressure vessel, and burst pressure is like the burst. It's like a pressure where the pressure vessel is going to burst. So it's a more pressure than obviously the design pressure and the operating or working pressure.
Okay, good. Thank you. Richard, would you like to add anything to this?
If you're talking about the last question, I would say, to me, a burst pressure is associated with a destructive test. You would find a destructive test performed on various pieces, which are very hard to analyze mathematically. I'm thinking of small valves, fittings, that kind of thing, where the testing procedure is still relatively affordable, and you're going to produce a large number of them. From the burst pressure, then you would then pick a working pressure, and the authority having jurisdiction would then have to approve that.
Yeah. So Richard, there is a comment slash questions to do with this, and it says, it's an anonymous attendee. When you mention safety factor of 3, is that 3 times the noted pressure? i.e., if it's 200 psi design pressure with 3 safety factors, does that make burst pressure 600 psi?
Okay, I would say no. I see Nicco also wants to answer this.
Oh no, I just put the answer just to make sure that's being answered. But I'll let you go ahead and add on to it if you'd like, Richard.
Well, when we talk about a safety factor of 3, I believe we're more likely talking about the reference to the allowable stress in the code. For instance, you start off by saying in ASME section 8 that we have to look at the material properties, which are documented in section 2, and then we say, okay, what is the ultimate tensile strength in section 2? We divide that by 3.5 to find out one option for the allowable stress. Then we also look at the yield stress in section 2 and divide that by 3. So to me, those would be the safety factors we would be looking at. That to me is what the safety factor of 3 or 3.5.
But thank you, Richard. We have quite a few questions, actually. They're still coming in.
Okay.
We'll see what we can answer. So next one I'm going to go to, because it is kind of related to the previous one. What's the difference between maximum allowable working pressure and design pressure? Can they be same? Can they be equal?
If you're asking me, I'd say the answer is yes. There doesn't have to be any factor of safety between the design pressure and the maximum allowable working pressure. You just have to make sure that every part of your vessel is capable of meeting that design pressure.
Okay.
Basically, the design pressure is what you start with. The maximum allowable working pressure is what you end up with when you've done all your calculations. and they can certainly be equal. There's nothing wrong with them being equal.
Okay.
Right. And just to add to that, it's actually similar to what we had done earlier, where we found that the shell thickness or the shell maximum allowable working pressure, if I can jump back quickly here, it might be difficult, but we found that the maximum allowable working pressure for the shell was higher than the head, and the head had a lower maximum allowable pressure. Therefore, that would be actually designated as the maximum allowable working pressure if we were to only look at those components.
Okay, I just want to make one more comment, sorry, and that is the maximum allowable working pressure will not be the normal operating pressure, because your system usually has to have some sort of a relief valve. So your maximum allowable working pressure will be the pressure which the relief valve achieves full flow. But full discussion, that topic's for another session.
Yeah. Thank you, Richard. There is the question about the destructive testing. Richard, you may remember at one point when we were bringing some vessels, vessels from overseas, and we wanted to register them as fitting across Canada, we had to do a destructive testing of the whole vessel. So the question is something related to this. The person is asking, is destructive testing performed on test coupons or on the complete vessel itself? If on the vessel, would this not destroy the vessels and require starting over?
Well, it depends on the nature of the destructive test. Nicco mentioned earlier impact testing. Impact testing is always done on test coupons. Those test coupons are a standard size, and the amount of energy required to pass or fail a test is also specified in various codes. So that's an example of where you would test on coupons. Where you're testing small valves or perhaps a jacket assembly, it's economical to basically build up a mock-up, an example vessel or example fitting, and test one. Actually, usually you have to test more than one. Test those, record the results, and that's an example of destructive testing of a complete assembly.
Yeah, Richard, you're absolutely right. So when we were bringing those single bag housings from overseas, we were registering them as a fitting, and we did the destructive testing on the complete vessel, small vessel. Because
Okay.
they were registered as a fitting. Yeah. Related to that, the question is, what would be the benefit of registering as a category 8 fittings versus a pressure vessel?
I'm not sure that there would be any benefit. I believe that there's a limitation on fitting registrations of 10 years. So if you're planning on using something as I'm assuming that you pass the criteria for volume and for pressure. Now it may be that you do have a pressure benefit, that you can go above 600 psi and register something as a fitting, and it may be that the registration process may be simpler.
Yeah. Now, Richard, if I may add, what I have seen more from the manufacturing perspective, if you're based on the volume and pressure, if it falls under a fitting category, we have a choice, or our client has a choice to still ask to register that as a U-stem versus UM or a fitting. However, if you are registering as a fitting, I mean, since if the shop can self-witness and certify,
Okay.
but if you're building as a U-stamp and a pressure vessels, there are other steps that needs to be taken care of. Nicco, maybe you can add to it. If something is registered as a fitting, it is done and it's good for 10 years. And every time we're building it, we could
We could
So
self-inspect, that's correct, yes. With the vessels,
Yeah.
we're bringing in the authorized
you don't
inspector.
have to call the ASME inspector every time to come check the material, come approve the material and approve the drawings for fabrication, because it's registered, we could do it over and over again.
Yep, that's correct, Anita. For a fitting registered with a, a UM stamp, there is no inspection required by the authorized inspector, and it's just the fabrication shop that can do the certification themselves, as you said.
So that's the benefit, so that your fabrication timeline and delivery will be a lot more, I would say, faster than building a U-stamp pressure vessel. Is
Yes, that's
Yep.
correct.
that correct? Okay.
Yeah.
Do we have time? We have a couple more minutes. Is CRN required for 2 water applications operating at 28 Celsius and second at 100 Celsius?
I believe Nicco touched on this in one of his slides. I'm looking at a printed copy. You say this is water. So we're looking at the figure 1A for liquids that are not more hazardous than water. So this would be the one on the left. So you can see that, see the diamond there where it says greater than 65 Celsius, Nicco? The one on the
Yep.
left? Yeah, okay. So the first application that the questioner is talking about is operating at 28C. So in that case, you would follow to the left because registration is it's not greater than 65. So you go here to the right, and then you have a choice. The question doesn't say what the pressure is, but let's assume that the pressure is less than 250 psi. In that case, the vessel would not require registration. However, for the application where it's 100C, then no choice. He has to go forward, and regardless of the pressure, there may be an option to register a fitting depending on what the volume is and so on. But registration does have to take place in some form if it's 100 Celsius.
Okay, thank you, Richard. There is another very good questions coming. Sulfur filter, steam traced. Does this vessel require CRN and APSA registration? When somebody says sulfur filter, I assume it's sour service. And the person is asking about APSA, so I assume it is in Alberta.
Mm-hmm.
So if it's a sulfur filtered steam trace, does this vessel require CRN and APSA registration? I guess the answer would be yes.
Yes. Well,
Yeah,
again,
I would
it is
think
noted.
so.
Sorry.
Yep. Now, if it is being fabricated outside of Canada, the only time it comes into play really for CRN registration is if it's being installed in Canada. Because again, the CSA B51 is pertinent for vessels installed within Canada. And if it's being exported elsewhere, it may not be necessary. So
Yeah, so the person put it there, it is installed in Canada. So irrespective of where it is built, the fabricators need to apply for CRN registration.
Yes.
Yeah, and they should do that before they start building anything.
Yes, exactly. Yes.
Mhm.
Yeah. I mean, our shop is in Canada. Our shop is in Cambridge, Ontario. So I think we have a little bit of advantage of that, knowing the procedures. Yeah.
Mm-hmm.
There's one more questions here. What mandates RT3 versus RT1? And Nicco, I think you had a slide there. You might want to go back to.
Yeah, the slide that was presented doesn't necessarily explain when it is required. And Annie might be able to shed more light into this, but what usually dictates spot radiography, or in this case, RT1 full radiography. If you're dealing with lethal fluids, it's full stop, full radiography. You do have no choice for at least vessels to be installed in Canada. And this is tying into the charts that we were looking at earlier, where for lethal vessels, you have to register it, and then within the CSA B51 code, as well as the ASME code, it does mandate full radiography.
Nicco, I think Zlatko is on the panel. Zlatko, would you like to add something if you're there?
For the with the radiography, it depends on a designer when he designs that you can actually use. If you want to lower the thinner the material, you can go with a full radiography, which is up to a designer, or it depends on the pressures and the temperature that the code will tell you, hey, you have to do the full RT, and it depends on a customer. Customer can come and say, hey, I only want a RT3 or RT4 or a full radiography. I just had one sample in here. The drawing asked for a spot. The customer, he came back, I want an RT4. So that means you have to do additional segments of the RT on a vessel.
Right, and just to add on to that, like Zlatko had mentioned, in particular between spot radiography and full radiography, it's kind of a costing evaluation here where there's a cost benefit analysis where, yes, you might pay more for full radiography, but the benefit you get from that is you're able to get away with thinner material, and obviously that also leads to thinner, less welding, etc. So it's something that should be also considered.
Okay, so it says, so I don't know if listeners, everybody knows Zlatko joined in a bit later as a panelist. Zlatko is our shop manager with 30, 40 plus years of experience in manufacturing pressure vessels. So everybody else on the panel list says we may sound a lot more theory when we're talking, but the practical experience is coming from our shop manager. And I think we're pretty much running out of the time here. Nicco, if you want to do any conclusion on it.
Yeah,
One question came in if you want to answer that. Is joint efficiency a function of weld quality, the metal itself, or the extent of radiography? Spot, partial, or full?
Efficiency of the radiography. Spot radiography, RT4, full radiography, those are joint efficiency. It doesn't have to do with the metal.
Weld quality. Okay, so the answer is the joint efficiency is a function of the extent of RTs, not the function of weld quality.
Joint efficiency is 75%, you got 85%, 100%, which is code 1. Same, the spot RT, which is RT3. With the RT4, you're just taking an extra 1 or 2, it depends on a customer with his requirements, or he will come, hey, I don't just want a spot RT, I want to have an extra 2 or 3 pieces. So when you actually stamping it on your plates, you have to specify by the code, is it RT3, RT4, or RT1? What did you do on that vessel?
Okay, sounds good. So I think, Nicco, unless you want to say something in conclusion, we will still be able to answer questions if, the email's there. Please send. And
yeah, no, and again, thank you everyone, and appreciate your time and your attention. It's something that again we've only gleaned the surface here. So if you do have any questions that might pop into your mind afterwards, feel free to fire off any questions that you might have. We're open to answer any questions.
thank you, everybody. We'll see you again soon. Thanks.